Okay. Welcome to the last class of material, new material for today. We're going to be talking about the problem of optimization, finding maximum and minimums for variables with two inputs. Okay. So first thing, recall our discussion before when we talked about maximum and minimum. They came in two different types, right? There was global and there was local. So if we have a local maximum, here perhaps, when we had just one variable, we had things that look like this, right? This was a local minimum because there was a neighborhood where this was the lowest point. This was a local maximum because there's a nearby, it's the highest thing. It's like you're on top of a hill. As distinct from a global maximum and minimum means that it's the greatest value for any x. And so these ones aren't global maxes and minimums. I have to change the function to look like something like this. If I do that, these are indeed the greatest and least values, and that is the global maximum. So the problem of optimization is finding the global maximum. Okay, it's finding the global maximum if what you want is a maximum. It's finding the global minimum if what you want is the minimum. So you might want to maximize profit. You might want to minimize material used to build something. Okay. So just like before, the strategy is to find the global maximum. You first find all the local maximums, and then that's just going to be a small list of things, and then that's going to tell you where the global max is. You've also, of course, remember, got to worry about what happens at the endpoints, because we saw things like this. So even though this is the only local maximum, it's not the global maximum, right? Because as x goes to negative infinity or x goes to infinity, the values get bigger and bigger. So you have to worry about that a little bit. But the basic problem is finding local maximums, finding the best to be the global maximum. Or if it's finding a global minimum, finding the local minimum and doing the best job you have there. Okay, so it's the same thing that we did before. Now we're just in the land of two variables. And so instead of maximums looking like this, maximums actually look like a genuine hill, right? Because we think of functions of two variables as we think of that as some kind of terrain. Okay, so that's actually not that hard to think about. Okay. So again, we do things graphically, numerically, and by formulas. Doing things graphically. Well, typically what we have is we have some kind of contour map like this. And so to find the global maximum and minimum, it's just like you're just doing a little search. And so here, okay, oh, this is a hard one. You've got to know our states. Does anyone know their states? Okay, find the maximum, minimum daily high temperatures in the states of all those states there. Well, firstly, let's find the global max and the global min within the US. Okay, so we look and we see what's the biggest contour. The biggest contour is here. This is like the 100, right? So down here, the southern border, it must be more than 100. Okay. So that's Big Bend, isn't it? Anyone been to Big Bend? Okay. One of my wishes is to go to Big Bend. It's either there or there. I can't remember where. That's the Rio Grande. So that looks like, so the places which is furthest away from the 100 contour line might be here and here. So that would be my guess for what the hottest place in the US at this point is. What about the coolest? Okay, let's have a look. So what's the smallest contour? Can anyone find? It's 60s, right? And so there's a little bit of 60s here. Okay, and then, ooh, it's all this thing here. Again, I'm betting Montana. Okay, that's the furthest point from the 60 contour line. So my guess is this is going to be where the global minimum is. But we can do the same thing for each state. So Mississippi is this one. It is, isn't it? Okay, good. Okay, so what do we think about the max and min there? Okay, so here is the 80 contour line. Here is the 90 contour line. It's going to be in the 80s. Okay, and is it going to be high or low 80s? High, right? So the coolest spot might be kind of here. That's the furthest away, it's the closest to the 80. So that might be, I don't know, I guess maybe 86. And over here, maybe 88, something like that. So you just have to use a ruler, and you have to kind of measure things from contours, and you just have to make the best guess you can. If you get a map with more contour lines in it, then you can make better guesses. But we've always known that, right? The finer the grid you have, the better the answer can be. Alabama is next door, isn't it? So that's this one here. Okay. Or it's right next to the 90. So it looks like it might have a top of 90, and it also be the same bottom there, 86. Pennsylvania, what do we got? Pennsylvania is here. It's right by the 90 contour line. So there's a 90 there, and it's a 70 there. Okay, that's a bit weird. Between 70 and 90, so Pennsylvania has a lot. New York is here. So it is in a, it's got a 70 here, an 80 there, 70 there, 80 there. So it actually looks like 80 is around where the top temperature might be. So anyway, so you just go through and you just use your eyeballs to have a check. Okay, so what happens if we've got a formula? So let's have a nice simple function, fxy x squared plus y squared. Okay. So this is kind of like a parabola, except it's a kind of like a parabolic well. Kind of see, and we kind of know where the minimum is already, right? Because squares always have to be positive. So when this when x is 0 and y is 0, then the sum is going to be 0. So that has to be the minimum value. And there's no maximum, right? Because we can always, whenever we find a point, we can always find a higher point. Okay. So let's just do taking derivative and setting it equal to 0. That's worked in the past. Let's see if it'll work now. So fx, what's the partial derivative of this with respect to x?
X plus
2x. We're keeping y constant. When we take the derivative of a constant, what happens to it? Goes away, right? So this is like, if we keep y constant, then it's like x squared plus c. Take the derivative of that, we just get 2x. Take the derivative with respect to y, we get 2y. Again, the x squared is a constant with respect to x. Set that equal to 0. X equals 0, y equals 0. It works. Let's think for a moment why it worked. So we know what this thing looks like, right? It looks like a parabola, but it's, sorry, this is pathetic, but anyway. It kind of looks like some kind of bag that you might have, right? Kind of like this. What did we find? We found the partial derivatives is 0. And we found that at this point, all the partial derivatives was 0. And that's the minimum. Does that make sense? Well, it does, because we go in the x direction, and what is it? It's flat. We go in the y direction. What is it? It's flat. So if it's flat in the x direction, it's flat in the y direction. Around there, it's flat. That's what we expect at an optimal point. Why isn't this point a minimum? Well, if we look at it, say we're at the point 1, 0. Okay. In the y direction, it's flat. But if we go in the x direction, the slope is 2. So that means like we're like on the side of a hill. It's sloped 2 this way, it's flat this way. So if we go this direction, of course we don't change the function, but if we go in that direction, we're climbing up the hill. If we go in that direction, we're climbing down the hill. We can find smaller and greater values. So just like in the one-dimensional case, to be a local max or a local min, you have to be flat, or the derivative not existing if you like on a corn or that. But we're not playing with those functions. We're just playing with functions you can take the derivative of. Okay. And just like before, you can't be at an endpoint. Now, the problem when you're doing multivariable is that endpoints become a lot bigger, right? Before, endpoints, there were just 2 points at the endpoint. Here, an endpoint, a boundary can be an entire curve. So that makes life a little bit difficult for us, but we're not really going to spend too much time worrying about that. We're just going to be looking from local maxes and mins and trying to figure out from that whether they're global max or mins. Now, the thing is, both partial derivatives have to be 0. Because if it's flat in both directions, they're kind of perpendicular to each other, that means they're flat in all directions. where if it's only flat in one direction, it's possible for there to be not flat in another, in perpendicular to it. And what do we call these points where every derivative is zero? We call them critical points, just like we did back when we did it in chapter, when was it, 4 or 5, something like that, chapter 4, I think. And of course, just because you've got a critical point doesn't mean that you have a max or a min. So, for example, remember in the one-dimensional case, we had a function like x cubed. This was a critical point, but it wasn't a maximum or minimum, right? Because if we would go in this direction, we decrease. If we go in that direction, we increase. Just like that, we can have things in the multivariable case, which are also kind of like those things. Think of a saddle point. So that's a curve that kind of looks like this in one direction, and like that, perpendicular to it. I hope you understand. See where it's kind of like a mountain pass. So here is, we're going off, there's mountains up here on either side of us, and we come up here, we go up, and then we go down. So in this direction, it's a maximum. In this direction, it's a minimum. But when we consider it as a whole, it's neither a maximum or a minimum. So, basic problem that I'll ask you to do is I'll give you a function. I'll ask you find the local maximum, local mins. Or we'll find the critical points, first of all, and then classify them. Are they going to be local max or are they going to be local min? And then you look at those and you feel like, well, which one of those is going to be the global max? So, the other thing is, how can you tell whether something is a max or a min? So if we go back to our example before of x squared plus y squared, is equal to 0, the critical point is 0, 0. And we can tell just by looking at it that it's going to be a local minimum. Just because it's in relation to a parabola. What we can do is we can do the second derivative test. This is kind of like, remember in one variable we had a second derivative test, which said, like for example, if you have a look, fx is x squared, the derivative is 2x, so x equals 0 is the critical point. If we look at the second derivative, it's 2, and that's positive. So that told us that this critical point was a local minimum. Does everyone remember that? Okay. We can do the same kind of thing here. We can look at the second derivatives. So fxx equals 2, fyy equals 2, fxy equals fyx equals 0. And the quantity you look at for the second derivative test, so this is the one place where it gets a little complicated, is you look at fxx, fxx times fyy minus fxy squared. Okay, so in this case here, it's 2 times 2 minus 0 equals 4. It's positive, so it's a local minimum. So you just get a more complicated version of the second derivative test. So that's the main formula that you have to remember. Oh, sorry. It's positive. So that means it's a local minimum or a local maximum. And then you go and you have a look at fxx and fyy, and the fact that fxx is 2 means that's why it's a local minimum. If you get something like x squared minus y squared, you get fx equals 2x, fy equals minus 2y, fxy equals 0. Set it equal to 0, you get a critical point at 0, 0, because that's when they're both equal to 0. You look at the second derivative test, fxx times fyy minus fxy squared, you get minus 4, right? Because fxx is 2, fyy is negative 2. That's negative, so that means you've got a saddle point. And the reason why it's a saddle point is because in one direction it's a minimum, and the other directions it's a maximum. So combined, we have a saddle point.
What is the fxy? Like, just what is that?
This,
Yeah.
that's the mixed partial derivative. So you take the derivative with respect to x, and then you take the derivative with respect to y. And so in this case, it's 0.
Wait, so is it on the first one? So you have fxx equals 2, fyy equals 2, and how is it 0 on that one?
On this one, so take the derivative of this with respect to y, it's 0. Take the derivative of this with respect to x, it's 2. Take the derivative with respect to this, a y of this, and it's 2. Take the derivative of this with respect to y, it's 0. Take the derivative of this with respect to x, it's 0. So that's the meat of the point of today's things. So this is the saddle points that I was talking about. So this is be something like a function like x squared minus y squared. So we can tell that it's a saddle point, right? Because at this point here, if we look at the slice, the vertical slice, it goes 305, it's going up, then 500, and then it's going down. So in this north-south direction, we have a maximum at this point. But if we look at the east-west direction, we see that it's going down, 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 down until we hit the bottom, and then it goes up, up, up. So in one direction, it's going up. The other direction, perpendicular, it's going down. So that's what we mean by a saddle point. And at those saddle points, you always have this quantity being negative. So if it's positive, it means it's a max or a min. If it's negative, it's a saddle point. If it's 0, it's inconclusive. Okay, so let's just do a couple of examples then. These ones are a little bit more complicated than before. So this is kind of like a basic problem from this section is I give you a problem, you find the critical points and you classify them. So that's what you need to be able to do for the test coming up. Okay, so what's the partial derivative with respect to x?
Two x plus 6.
2x plus 6. Excellent. Partial derivative with respect to y?
Two y minus 10.
2y minus 10. Right, so then fxx is what? 2, yep. fyy, fxy, and when we take the derivative of this with respect to y, what do we get?
0.
Yep. Excellent. Now we've taken all our partial derivatives. Now we can find the critical point. We set this equal to 0. And what do we get? We get that x is minus 3 and get y is 5. So there's one critical point at minus 3, 5. We want to classify it. Well, we do the second derivative test. We call that d. It's 2 times 2 minus 0 squared is 4. It's positive. So that means it is either a max or a min. And then when we look at these guys, we see that it's a min. Okay, so second derivative being positive means that it's concave down in that. So it's concave down in this direction, it's concave down in this direction. So it's a minimum. Okay, so now let me stop the share here. Let's go over here. Does it go that far? No, it doesn't. Okay. Okay, so let's do a second one. We want it to be x cubed plus y squared minus 3x squared plus 10y plus 6. Okay. A little bit more complicated. So let's take the partial derivative. 3x squared minus 6x. Fy is 2y plus 10. Okay, so we set that equal to 0. This tells us that y equals minus 5. This one, what's that? 3x, x minus 2 equals 0. So x equals 0 or 2. So now we've got two critical points. We've got 0 minus 5, and we've got 2 minus 5. Okay, to investigate further, we take more derivatives. So fxx is 6x minus 6. Fyy is 2. Fxy is 0. So for this one, D is, we plug in the values here. Fxx is minus 6. Fyy is 2. Minus 0, it's minus 12. So that tells us that this is a saddle point. Whereas this one, D equals 2 times 6 is 12 minus 6 is 6. It's 6 times 2 minus 0. It's 12. So it is either a max or a min. And we go and we see that the second is it's concave down. In the y direction, it's concave down. I feel like I'm doing a dance up here. It's how do people think about that one? A little bit harder, but it's the same kind of deal, right? Let's do another one. Let's just write it down here. Was it x squared minus 2xy? Oh, this is a little bit different. Plus 3y squared minus 8y. And it's different because now we've got xy terms. So when we're going to get different kind of answers from before. Elijah, what's the partial derivative of this with respect to x? Yep. Minus 2y, exactly right. No other x's there. Great. Hannah, what's the partial derivative with respect to y?
Minus 2x plus 6y.
Exactly right. Okay. Okay, we set it equal to 0. Oh, this is a whole lot more complicated, right? Do people remember doing simultaneous equations? Okay, so this tells us that x equals y, for this to be 0. And this tells us that minus x plus 3y equals 8. If x equals y, then we can replace minus x by minus y. That's 2y equals 8. So y equals 4. X has to equal 4. Okay, so 4, 4 is the critical point. Do people remember doing problems like this back in algebra? You should. Okay, so then we've got to find d. So fxx. Okay, we take the derivative with this with respect to x. What do we get, Peyton?
2 minus 2y.
Nope. Remember, y is treated as a constant.
So
Just 2. Yeah. That's a hard thing to. I just beat it into you. Ellie, what's the derivative of this with respect to y?
Wouldn't it just be 6?
It is just 6. And suddenly we get an fxy. Can anyone see what fxy is? So what's the derivative of this with respect to y? Well, -2. Or the derivative of this with respect to x? It's also -2. Okay, and so now d equals 2 times 6 minus -2 squared is 12 minus 4 is 8. It's positive. So therefore, the critical point is either a max or a min. They're both positive. So again, we've got our bowl. This is a local min. Okay, that was a little bit harder, right? We had to do a little bit more work.
For the f of xy, they're both negative too, but do you like add them, or I guess is it going to be the same for both of them?
So they're always going to be the same. So this is actually fxy times fyx. That's why. But they're always the same, so they always get squared. Okay. I think we've got time for another problem. 400 minus 3x squared minus 4x plus 2xy. And here's the most complicated one yet, minus 5y squared plus 48y. Okay. Fx, we just go through, that goes away, minus 6x, minus 4, plus 2y, 0, 0, because they're constant. Okay, damn, we get another mixed thing. So anyway, Fy, 0, 0, 0, plus 2x, minus 10y, plus 48. Okay, so this is, have to remember how to do this, but we kind of do. So that tells us that minus 6x plus 2y equals 4. And 2x minus 10y equals minus 48. Do people remember the kind of strategies you should do? So you've got to eliminate a variable. So let's eliminate the x. So we multiply this by 3. we'll get a 6x here that we can then add to that to get rid of the x's. So multiplying that by 3 gives us 6x minus 30y equals minus 144, I believe. So if we add those two things together, the 6x's cancel, we get minus 28y equals minus 140. So multiply through by minus 28, we get 5. So y equals 5. And then when you've got 1, you can find the other, right? Because minus 6x plus 10 now equals 4. So minus 6x equals minus 6. So x equals 1. That's a lot of work. But we found that 1, 5 is our critical point. Now we can analyze it. Okay, fxx. Somebody? Derivative of this with respect to x? Elijah? Negative 6. Fyy. Ellie? Negative 10. Fxy. Either the derivative of this with respect to x or the derivative of this with respect to y. We get what? 2. Yep. So d is now minus 6 times minus 10 minus 2 squared is 56. It's a positive, so therefore it's a max or a min, but now we look at these things, they're negative. So they're like this now. That means we have a max, right? Okay, so that was kind of hard work, I think. So there'll be a few problems for that on the homework. And so we don't meet. Monday, we'll meet in the lab. We'll talk about your projects and you show me what you've done and I'll help get over any blocks that you've had. Oh, I should have, we can then assign times at the end of the week. And okay, so the test is going to be Tuesday week. It's going to be 2 parts. The first part is going to be chapter 8. And it's just going to be like a normal test on chapter 8, just like the other ones. Second part is going to be a comprehensive test, but that's going to consist mainly of short questions, so multiple choice, short answers. Any questions about anything?
That's on Tuesday.
That's on Tuesday. What is it? May something. Is it May by then? It must be May by then. And it's like 7:30 in the morning in this room. Okay. That was a hard class. I had to actually do some math.